Welcome back to AI.Code.Cast. Ready for another deep dive? Today we're tackling a classic coding interview problem, one that you'll definitely want to have in your back pocket, especially if you're prepping for those tech interviews.
You got it. It's one that seems pretty basic on the surface, but it's got some interesting twists and turns, that's for sure. We're talking about adding two numbers, but there's a catch. Those numbers, they're represented as linked lists.
Oh, linked lists. Those can be tricky. Before we jump into the problem itself, can you give us a quick refresher on linked lists for anyone who might be a little rusty?
Absolutely. Picture a chain, like a chain of nodes. Each node in that chain holds a piece of data. In our case, it'll be a single digit. But here's the key. Each node also has a pointer. Think of it as a little arrow that points to the next node in the chain. It's like a treasure hunt where each clue leads you to the next.
Okay, so we've got this chain of nodes. I'm with you so far. What's the head of the linked list? Is that like the beginning of the chain?
Exactly. The head is your starting point, the first node in the list. Now, back to our problem. Each of these linked lists is going to represent a number, but with a twist. The digits are stored in reverse order.
Reverse order. So it's not just a straightforward representation of the number?
Right. Think of it like this. If you wrote the number 342 on paper, but flipped the digits around to 243, the 2 would be the head of the list, the 4 would be the next node, and so on.
Ah, okay. So the head of the list represents the least significant digit in the number. Makes sense. So what's the actual task here? What are we supposed to do with these linked list numbers?
The goal is to add them together, and the result, that should be another linked list, also in reverse order. So if you were adding those linked lists representing 243 and 564, the output would be a brand new linked list representing 708.
Okay, I think I'm starting to get the picture. It's not as simple as just adding the numbers directly. We need to figure out how to navigate these linked lists, extract the digits, add them correctly, and then build a whole new linked list with the answer.
You got it. Now, let's put on our thinking caps and brainstorm how we could approach this problem. What's the first, most basic approach that pops into your head?
Well, if I were working with regular numbers, I'd just add them up the way we learned in grade school. Can we do something similar with these linked lists?
We could. And that's actually a common first thought. We call it the brute force approach. Basically, we'd convert each linked list into its corresponding integer, just like you'd read it off the chain. Add those integers together like we normally would, and then convert that sum back into a linked list.
Let me see if I've got this straight. So let's say we have that linked list, 243. We'd go through it, pull out each digit, and put them together to get the integer 342. Do the same thing with the other linked list to get 465, add those together to get 807, and then finally create a new linked list to represent that 708. Is that the gist of it?
You nailed it. It's a completely valid approach. It'll definitely give you the correct answer, but there's a catch. It might not be the most efficient way to solve this problem.
Why not? It seems pretty straightforward to me.
The issue is all the back and forth conversion we're doing between linked lists and integers. Every time we do a conversion, we have to go through the entire linked list, which takes time. And what if those numbers are super long? We might run into problems trying to fit the integer representations into our computer's memory.
So, while the brute force method gets the job done, it's not going to win any awards for speed or efficiency. Is there a more streamlined way to approach this? A way that works more directly with the linked lists themselves?
Definitely. Let's think about how we add numbers by hand, digit by digit. We start from the rightmost digits, add them up, and carry over anything that's greater than 10 to the next column. Do you see where I'm going with this?
I think so.
Oh.
Are you suggesting that we could mimic that same process but directly on the linked lists instead of converting them to integers first?
Exactly. Just like adding on paper, we'll need to keep track of any carryovers as we go. And for each pair of digits we add, we'll create a new node for the sum and link it to our result list.
That makes sense. So we start at the heads of both linked lists, add those digits, and if the sum is 10 or greater, we carry over a 1 to the next pair of digits.
You're on the right track. And remember, each time we add a pair of digits, we create a new node in a result list to store that sum.
Okay, got it. We create the new node, link it to the previous node in the result list, and then move on to the next pair of digits in our input list, carrying over any extra ones if needed.
That's the idea. We'll keep moving through both lists, digit by digit, adding, carrying over, and creating new nodes for our result list. It's like having two runners, one for each linked list, moving step by step and adding the values they encounter along the way.
Okay, so we've got this idea of walking through both lists simultaneously, adding digits and handling carryovers. This method seems pretty intuitive. It's almost like we're directly translating the way we add numbers on paper into code. But I'm curious, what do we call this approach?
This is called the iterative approach. It's a common way to solve problems that involve going through a list or sequence step by step. It's a good starting point for problems like this, for sure. But before we get too deep into the details, are there any potential pitfalls we should be aware of? Any tricky situations that might pop up?
That's a good point. Well, one thing that comes to mind is, what if our two linked lists aren't the same length? What happens if we run out of digits in one list before the other?
That's a fantastic question, and it's definitely an edge case we need to be prepared for. If one list is shorter, we can simply treat those missing digits as zeros, just like we would if we were adding on paper.
Right, so it's like adding a leading zero to the shorter number to make the columns line up.
Yeah.
Okay, that makes sense. Anything else we should be careful about?
Remember those carryovers? We need to make sure we handle them properly, even after we've processed all the digits in both input lists.
You mean if we get to the end and there's still a carryover, we need to create one more node at the beginning of our result list to represent that final one?
Exactly. It's just like when you add 99 and 1. You get 100, and that leading one is essentially a carryover from the previous digit addition.
Okay, so we always check for any leftover carryovers at the end and create a new node for it if necessary. Got it. So far, we've talked about this step-by-step iterative approach. But are there any other ways to solve this problem? Maybe something a little more elegant, even if it takes a bit more brain power.
You're in luck. There's another technique that might just fit the bill. It's called recursion. It's where a function actually calls itself. It can be a little mind-bending at first, but it can lead to some really beautiful and concise solutions.
Recursion. Okay, I'm intrigued, but also a little intimidated. How would we apply recursion to a linked list problem like this?
Think about it this way. At each step, we need to do the same thing. Add the corresponding digits from the two lists, taking into account any carryover from the previous step. And then we repeat that same process for the next pair of digits. Do you see how this repetitive nature might lend itself to recursion?
I think I see what you mean. We're essentially breaking the problem down into smaller, almost identical subproblems. Each subproblem is just adding a single pair of digits and passing any carryover to the next subproblem.
Exactly. We can create a recursive function that does just that. It takes two nodes, one from each linked list, along with any carryover, and adds those digits together. It creates a new node for the sum, and then here comes the recursive part. It calls itself to handle the next pair of digits.
Okay, that makes sense. So each recursive call is handling just one pair of digits and passing the baton, along with any carryover, to the next call. But what about that carryover? How do we make sure it gets passed along correctly within those recursive calls?
Great question. We can include the carryover as a parameter to our recursive function. So each time the function calls itself, it passes the updated carryover value along. It's like attaching a sticky note to the baton as it gets passed.
I love that analogy. It helps me visualize how that information flows through the recursive calls. But what happens when we get to the end of our linked lists? How do we tell our recursive function to stop calling itself? We don't want it to go on forever.
That's where the base case comes in. The base case is the condition that tells the recursion, okay, you've done your job, time to stop. In our case, the base case would be when we reach the end of both linked lists.
Okay. So when both input nodes are null, meaning there are no more digits to process and there's no carryover left, that's our signal to stop the recursion. But wait, we're trying to build our result list in reverse order, right? How does recursion help us with that? It seems like we'd be building it from the end to the beginning.
That's where the real beauty of recursion shines. Think of each recursive call as returning a piece of the solution, a node that represents part of the sum, and it starts from the least significant digit. As those recursive calls start to return, they're essentially building our result list from the tail towards the head.
So as the recursion unwinds, it's like we're constructing our result list in reverse order, just as we need it. It's almost like building a house from the roof down, isn't it?
That's a great way to put it. Each recursive call adds another layer to our solution, and the final call gives us the base, the head of our result list.
Okay, this recursion thing is starting to click. It feels a little magical, building the solution in reverse like that.
Yeah.
But I'm guessing there are still some tricky parts to figure out, right? Just like building a house upside down, I bet there are some unique challenges.
You're absolutely right. There are a few things we need to consider carefully, especially when it comes to those edge cases we talked about earlier. But those are topics for another time on our next deep dive into this fascinating problem.
I can't wait. This has been a great introduction to the challenges and possibilities of adding numbers represented as linked lists. Thanks for walking us through it. And to all our listeners out there, Be sure to join us for part 2 of this deep dive, where we'll explore those recursive solutions in more detail.
See you then.
Okay, so where were we? Yes, linked list addition. We talked about some of the potential pitfalls of this problem, like dealing with linked lists of different lengths and those pesky carryovers. But I'm eager to dive into the actual solutions. Let's start with that iterative approach, the one where we walk through the linked lists step by step. How will we go about implementing that?
Well, we need a way to keep track of a few things as we move through the lists. First, that carryover, right? We'll need a variable for that, let's call it carry, and we'll initialize it to 0. And of course, we'll need to keep track of our result list as we build it.
So how do we actually start building the result list?
Yeah.
Do we create a new node for each sum as we go?
Exactly. But there's a neat trick we can use to simplify things. We'll create a dummy node to act as the head of our result list. It won't actually hold any data from our calculations. It's just a placeholder to make things easier.
I see. So we have our carry variable, our dummy node for the result list.
Yeah.
What's next? How do we know when to stop processing the input lists?
We need a loop, right? A loop that keeps running as long as we still have digits to process. So as long as either of the input lists is not empty or we have a carryover value that's not 0, we keep going.
Okay, I'm following you. So inside this loop, we're grabbing the digits from the current nodes of our input lists. And remember, if one list is shorter than the other, we'll treat those missing digits as zeros. What happens next?
Well, we have our digits. Now it's time to add them up. We add the digits from the current nodes along with any carryover from the previous step. That gives us our sum.
Right, but that sum could be greater than 9, meaning we'll have a new carryover for the next step. How do we handle that?
Easy. We divide that sum by 10. The whole number result of that division becomes our new carry value. And the remainder, sum modulo 10, is the digit that goes into our result list.
Clever. So we create a new node for that digit, the remainder after the division, and we append it to our result list.
Exactly. We link it up to the previous node in the result list, and then we're ready for the next step. We advance our pointers to the next nodes in the input lists, and the loop continues.
This loop keeps chugging along, adding, carrying over, and building up our result list node by node. I can see how this iterative approach is really methodical, just following the steps like we would with pen and paper. But what happens when the loop finally ends? Where's our final result?
Remember that dummy node we created at the beginning? Well, the next pointer of that dummy node is now pointing to the head of our result list.
That's why we use the dummy node. It acts as a convenient anchor for the beginning of our result list. Clever. So that's the iterative approach, breaking the problem down into small, manageable steps. Now, you mentioned earlier that there's another way to tackle this, recursion. Can we switch gears and explore that a little bit? I'm still a bit fuzzy on how recursion would actually work in this scenario.
Absolutely. Let's dive into the world of recursion. Remember, the key idea behind recursion is to break a problem down into smaller, self-similar subproblems. In our case, each subproblem is basically adding a pair of digits and passing any carryover onto the next subproblem.
Okay, I'm starting to see the connection here. So how would we actually define a recursive function to handle this?
Well, we'll need a function, let's call it addLists recursively, and it needs some information to work with. It'll take 2 nodes as input, one from each of our linked lists, and that carryover value, just like we had in the iterative approach.
So the function gets 2 nodes to add and the current carryover. What's the first thing it should do?
Well, before we start adding, we need to consider our base case. Remember, the base case is what tells the recursion when to stop. Otherwise, it would just keep calling itself forever.
Right, that makes sense. So what's our base case for this problem?
Think about it. When do we know we're completely done with our calculation? When we've reached the end of both linked lists, right? And when there's no carryover left.
I see. So if both of the input nodes are null, meaning we've run out of digits in both lists and the carryover is 0, we know they're finished. In that case, we can just return null.
Exactly. Returning null in this case basically signals that we've reached the end of our calculation and don't need to add any more nodes to the result list. But what if we're not at the base case? What should the function do then?
Well, we've got our 2 nodes, and we might have a carryover value. Just like in the iterative approach, we need to grab the digits from those nodes, treating missing digits as zeros if one list is shorter. Then we add those digits and the carryover to get our sum.
You got it. And just like before, we calculate the new carryover by dividing the sum by 10. Then we create a new node with the value of sum modulo 10, just like in the iterative approach. This is the digit that will be added to our result list. But here's where things get a little different.
Okay, I'm ready for the quiz. What do we do with this new node in the recursive approach?
Instead of appending it directly to the result list, we make a recursive call. We call our addList recursively function again, but this time we pass in the next nodes from the input lists and the new carryover value.
Whoa, so we're calling the function within the function. That's recursion in action. But what are we doing with the result of that recursive call?
That's the key. The result of that recursive call is going to be the next node in our result list. We attach it to the next pointer of the node we created earlier, the one holding the current digit sum.
So each recursive call is essentially returning a piece of the result list, starting from the tail and working its way up. I'm starting to see how this all fits together. But what about the very first call to add lists recursively? What does that return?
That initial call, that's the one that gives us the head of our result list. The recursion unwinds, each call returning a piece of the list until finally, that first call gives us the starting point, the head of the entire linked list representing the sum.
Wow, that's amazing. It feels like magic building the result list in reverse like that. But it also seems a bit more complex than the iterative approach. Are there any downsides to using recursion? Anything we need to be careful about?
Well, recursion can be a bit more memory intensive than iteration. Each recursive call adds a new frame to the call stack, which can lead to a stack overflow error if our lists are really, really long.
Right, that makes sense. It's like stacking up a tower of blocks. If the tower gets too high, it might topple over. But on the other hand, recursion can be incredibly elegant and efficient for certain problems. It's all about understanding the trade-offs and choosing the best tool for the job.
You got it. So we've now explored both the iterative and recursive approaches to adding linked list numbers. We've talked about the concepts, steps involved, and even touched on some pseudocode to represent those steps in a more concrete way.
It's been a great deep dive. We've covered a lot of ground, and I think I have a much better understanding of how to approach this problem. But I'm curious, are there any other variations or challenges related to linked list addition that we could explore?
You bet. We've only scratched the surface here. There are all sorts of interesting twists and turns we could take this problem. For example, what if the digits in our linked lists weren't stored in reverse order? How would that change our approach? Or what if we wanted to optimize for speed or memory usage even further? There's always more to learn and explore in the world of algorithms and data structures.
Right, like if the lists were in normal order. That would definitely throw a wrench in things. We'd have to think about how to align the digits properly before adding. But for now, let's stick with the reversed order scenario. We've talked about how to handle those cases where the lists are different lengths, and we know to watch out for that final carryover at the end. But I'm still curious, are there any other gotchas or tricky situations we should be aware of when working with recursion for linked list problems?
Well, one thing to keep in mind with recursion is it can sometimes be a bit more memory intensive than using a loop, like in the iterative approach. Each time we make a recursive call, it adds a new frame to the call stack. If the lists are super long, we could potentially run out of stack space and get a stack overflow error.
Ah, that makes sense. It's like stacking up a tower of blocks. If the tower gets too high, it might topple over. So with recursion, we need to be mindful of the depth of those recursive calls, especially if we're dealing with really large lists.
Exactly. But on the flip side, recursion can often lead to more elegant and concise code, especially when the problem itself has a recursive structure, like this one. It's all about choosing the right tool for the job, understanding the trade-offs, and making informed decisions based on the specific constraints of the problem.
I like that. It's not always about finding the one right way to solve a problem. It's more about understanding the different approaches and their strengths and weaknesses, and then choosing the best fit for the situation at hand.
Absolutely. And, sometimes the best approach might be a hybrid of different techniques. You might use iteration for certain parts of the problem and recursion for others, whatever makes the code the most clear, efficient, and maintainable.
I love that idea. It's all about being flexible and creative in our problem-solving process. Well, I think we've had a fantastic deep dive into this linked list addition problem. We've gone from the basics of what a linked list is to exploring both the iterative and recursive approaches to solving this specific challenge. We even touched on some pseudocode to illustrate how these approaches could be translated into actual code.
And we've talked about some of the important considerations, those tricky edge cases, and the trade-offs between different approaches. It's been a great discussion.
It really has. So to all our listeners out there, we hope you've enjoyed this deep dive into the world of linked lists and algorithms. Remember, understanding these fundamental data structures and how to manipulate them is essential for any aspiring software engineer. And don't be afraid to get your hands dirty and try implementing these solutions yourself. That's the best way to learn.
Thanks for joining us on AI.Code.Cast, and we'll catch you next time for another exciting coding adventure.
See you then.